here. All right, it does its job. So let's look at your next assignment, guys. This is going to be assignment 6, and it's going to be about a second order autoregressive model. That's what we're going to look at. So assignment 6 is going to be about the following. So we have basically a simplified structure, because only the past observation from at time point t minus 2 and not at time point t minus 1 is going to be relevant in this case. So this is still a second order autoregressive model, as you see. Okay, but the time lag here is t minus 2, or 2 steps actually, so it doesn't depend on the previous observation. And what you need to do is basically 3 things. Now, first off, you need to recognize that the lag polynomial of this model is going to be 1 minus c times a pseudo multiplication L squared, where L is the lag operator. You know what the lag operator is. And what I want you to do in the first case is I want you to develop a stationary condition for that parameter. Okay, so you need to examine at which case is that process stationary, what the parameter needs to satisfy to be considered a stationary process here for the model. That's number 1. Okay, so of course you know what the stationarity condition would be in terms of the lag polynomial, so you would need to basically apply that on that parameter. You can use a triangle conditions also if you like, so it's up to you. All right, so how would you basically determine? And of course, I would like you to please explain. So I might add here, please explain briefly. Okay, so you need to explain briefly your steps. Okay, not just provide the condition, but also to tell me a little bit, at least, how you come up with the condition. All right, so that's number 1. All right, number 2, and that basically based on that, assume that it's going to be stationary. And if it's stationary, then this means that the lag polynomial is invertible. So that means that the lag polynomial, basically the inverse of the lag polynomial, is going to be finite. We talked about that. And I want you to find that expression. Okay, so that consists of basically 60% of the total assignment, which is relatively large percentage, right? But I want you to basically to do this. And just to give you the hint behind that, because you will need to identify these coefficients. So every basically inverse of the lag polynomial is going to look like this. So you will basically determine that structure by telling me what these coefficients are. So what is C0? Okay, what is C1? What is C2? And so on. Okay, so that's something that you would need to identify and tell me based on that how it's going to look like. Okay, so again, you might remember the stationary condition. A autoregressive model is stationary if and only if the inverse of a lag polynomial is finite. You may remember that one. I was explaining you to basically to how and why and what's the intuition and all that stuff. Okay, so that is a stationary condition, and I want you to apply it explicitly on that model by telling me what these coefficients are. Okay, all of them. So I would basically get the idea, how would you do this? Okay, so let me tell you something. You would give the first 6, 7 coefficients, right? So then I would recognize the structure, or you would basically be able to identify that. Now, this is not, let's say, straightforward in that case, but you need to know that you can bypass the series, the Taylor series expansion. So usually you would basically do this by using the Taylor series, all right? But if you tried that, you would find that it's not that straightforward, okay? Think about the structure, and you will recognize why I left out the observation yt minus 1. So, okay, you would have basically 0 times yt minus 1 there, okay? Because that simplifies a lot of things. And if you recognize that, you'll also basically going to recognize that you can bypass the Taylor series expansion, which you would usually do when you would try to identify those coefficients. Okay, so that's something that I want you to consider. Okay, it will take time a little bit, so it will not be solved, let's say, in 20 minutes or so, but it's much easier than you think. Okay, so if I provide you with the solutions, you're going to see that it's going to be much easier. But think about it. Okay, so just keep that in mind. You can bypass the Taylor series expansion. Okay, so there is an alternative. And that has something to do with the structure of the lag polynomial, because it's relatively simple, although you might not see that as such, but it's going to be much, much easier as you think, okay? I'm not going to give you the idea how to bypass that, but think about conversion series, okay? So think about basically when would the inverse of the Lac polynomial, because that's considered to be a series, okay? So when would that series converge? You would recognize maybe that structure by putting everything together, okay? Have a look at the first order autoregressive process, how that was basically shown, okay, without looking at the Taylor series expansion explicitly. So I demonstrated it by means of the Taylor series, but I also bypassed that one. And have a look at that, okay, so just see how I was doing that, so maybe I can give you another hint. Okay, so check out basically how I was doing that with the first order autoregressive model by bypassing the Taylor series expansion. And you will recognize that you can do this too, okay? So that's going to be your assignment. And based on that, I want you to calculate the mean and the variance of the process, okay? Because looking at the structure, okay, so looking at the inverse of the Lac polynomial, you'll find, and then this is what it's going to be, that the structure of that process, I mean, it's going to look like this, right? So you have AL, let's say, times the process, which is equal to the noise. So the process itself is going to be identical, I mean, equal to the inverse of the Lac polynomial times the noise, let's say, okay? Again, if I say times, I mean a pseudo multiplication. Okay, so based on that, you can check what the expectation of that would be and what the variance of that would be, because that's what you would need to identify the variance, as I did, okay? And you don't need to basically assume that time is basically not bounded from below and this and that, so skip that assumption regarding time. That's something that you would not need to consider, okay? Regarding the autocovariance, that is difficult. Okay, I mean, that's not difficult, but it's maybe like, you know, structured. And then that's a certain way because you need to distinguish between different cases. But I'm fine with the mean and the variance, okay? If you provide the autocovariance also, then I will take that as a bonus, okay? But keep that in mind, it's not going to be more than 20% of your total assignment, so I will not going to be. Again, so the autocovariance is a little bit more, let's say, advanced because you need to identify the specific cases. However, you would need to know that the process is not autocorrelated with every single time lag there is, okay? And that has something to do with basically its form and its structure. It's an AR2 model, but without having the observation at time point t-1 directly as an impact or as a predictor in that model, okay? So there is going to be some cases where the time lag doesn't play a role regarding autocovariances. And if you want to provide this, I will give you bonus at 20%. Okay, so then you would have at least 60% of this assignment. Anyways, okay, so the deadline is going to be Friday next week. That is the 14th of June, if I'm not mistaken. So that's going to be that. All right, guys? Okay, so that is a theoretical exercise, as I'm aware of, but you need to do some theory too. Okay, so that's something that you would need to also consider yourself. Any questions based on that? No questions? All right, then I'm going to consider the final part of this lecture because today we're going to talk about how to write a paper and specifically, but I want to consider the remaining parts of an AR process that we left behind basically from last time. I wanted to do this last time, but I didn't have time for that. So if you look at the ARP model, which is, I mean, this is a general structure, as you might know. Okay, so that is, okay, epsilon is always a noise. Okay, and the last, basically, observation, which is a predictor, is going to be provided with the observation at time point t minus p. All right, p is, of course, some integer, some natural number, let's say, and then you can also express this by means of its Lac polynomial. The Lac polynomial, again, so this is always the structure of an AR process, okay? And this Lac polynomial is going to look like that. So if you change the structure of the Lac polynomial, you would also change the structure of the process as well. All right, so that's something that you would need to be aware of. Now, I want you to consider the following case. If the process is stationary, and that's what I'm going to look at, then its autocorrelation can be expressed differently. Okay, so I'm going to basically talk about that. This is how it's going to look like when it's come to the autocorrelation. You can calculate the autocorrelation by using previous autocorrelations or with respect to time lags. Okay, so keep that in mind. This is the notation for the autocorrelation if the process is stationary with respect to time lag h, of course, and this can be expressed by using previous autocorrelations as well. I'm going to demonstrate this, how this works. Okay, so you can, that is a, let's say, recursive expression. So if you know what this is and what these are, then you automatically know what the autocorrelation with respect to time lag is going to be as well. Because keep that in mind, if you want to do this, you can simply just, you know, skip the noise, and then you would replace basically the observations of the process by the autocorrelation function, and that's it. So this is how you come up with the idea, and then you can put basically the time lag h into that consideration. Okay, so let's say if you have an AR3 process, okay, and you know what the autocorrelations are with respect to, let's say, the time lag 1, 2, and 3, okay, then you also know what the autocorrelation with respect to time lag 4 is going to be, because that is going to be determined by the previous autocorrelation function structure. Okay, now when it comes to the first order autoregressive process, and that's what I'm going to look at. Okay, now before I start, I'm going to prove these Yule-Walker equation or Yule-Walker equations. There are multiples, but that's going to be one. Now, assume that the process is going to be stationary. If it's stationary, then you can simply just replace the time point t by time point t plus h. All right, so that's something that you can do. All right, which I do, by the way. And yeah, so assume that the process, I mean, we're going to assume that the expectation of the process is going to be 0. If you don't assume this, then it's going to work. So if I say without loss of generality, it means literally it doesn't matter whether the expectation is 0 or not. If it's 0, then it's going to be the simplest case. Why I'm assuming that? Because if you want to calculate the autocovariance of the process, which I'm going to, okay, so that is going to be basically the autocovariance, then it's simply just going to be the expectation of the product. Okay, and that's the reason why I'm assuming that. Again, and this is an implication based on from this assumption, right? Because the process is stationary around 0. Now, if it's not 0, what you can do, if you want to, what you can do is you can transfer the process. You can simply subtract the mean from it. If you subtract the mean from it, this is not going to affect the autocovariance, because the autocovariance does not depend on additive constants. You understand what I'm saying? So if that is not true, okay, then you can basically shift the process. So you can simply subtract the mean, whatever it is, because that's going to be a constant, since the process is stationary, right? So you can make it basically equal to 0 by simply subtracting a constant from it. But if you do this, that's not going to affect the autocovariance. Do you understand what I'm saying? Okay, so the autocovariance is not affected by additive constants. And so therefore, if you don't have 0 for the expectation, that's going to be fine. Let me check, okay, whether it is recording, because sometimes I'm not very convinced. Sometimes it's interrupted, but it seemed to work. All right, now, okay, now if you, again, so it does work if you don't assume this. All right, now if you, again, but if you do, then the autocovariance is going to be equal to the expectation of the product, as I mentioned before, because the autocovariance is the expectation of the product minus the product of the expectations. But if the expectations are 0 with respect to all time points, then it's simply just going to disappear. Okay, so if this is basically equal to 0, and that is also going to be 0, of course, because the process is stationary. So it doesn't depend on the time point. Expectation would be simply just the expectation of the product. I mean, the autocovariance, sorry, would be just simply just the expectation of the product. All right, now if you put that in, okay, so I'm going to basically keep that one. Okay, that's going to be inside the expectation operator, and I'm going to replace the observation at time point t plus h by this expression. That's simple. Okay, so then you simply just put it in, of course, inside these brackets here. Okay, so inside the expectation operator, I'm replacing the observation at time point t plus h by its structure as you see it. Okay, so just simply put it in, which I did. Okay, so that is going to be here. I keep out the constant, by the way. So I will take that out too, because I don't want to waste my time on that. Again, if we can take that out, because, I mean, if it's equal to 0, then the expectation is going to be 0. So you would take that out. But again, autocovariance is not affected by it. So if you don't take it out, it will work anyway. All right? So it doesn't basically mean anything. All right, so I was taking that out. Okay, so I will removing all additive constants if I consider variances and autocovariances. And then you just simply play the rule here of algebra. Okay, you simply calculate these products as I do. Okay, because if you multiply a sum by yt, then you would multiply every sum n by yt. Okay, that's not a surprise. So you have it here and you have it here. And that's that. Okay, and then of course you have it here with the noise as well, because the noise is also going to be multiplied by it. All right, and the expectation of a sum is going to simply just be the sum of the expectations. And plus the expectation of a linear transformation is the linear transformation of the expectation as well. So you can take out the constants, which I did. Okay, so I would take out these a's, let's say. And R left behind is basically these products. Okay, now, of course, you know, and you might be aware that there is no autocorrelation of, let's say, future observation of the noise with the current observation of the process, because the noise is going to be it's not going to be autocorrelated, right? So you know basically what the noise is. Noise is actually a stationary process with mean 0, with a constant variance, and with 0 autocovariance. And that's basically what it would be. This implies, on the other hand, that there is simply no autocorrelation with, let's say, some future observation of the noise and the past observation of the process. Okay, so that because this is going to be equal to 0 because of that. All right, now, and all you're left with is basically the autocovariances, okay, because that expression, again, is equal to the autocovariance, as I mentioned before. The process is stationary, all right, and then you have the time lag h minus 1 inside, all right, so this is basically with respect to the time lag h minus 1, and that is the autocovariance with respect to time lag h minus p, and so on and so on, and that is, of course, equal to 0, right, as I mentioned before. Now, you see that the autocovariances, okay, since the process is stationary, okay, I mean, the autocovariances do depend on the time lag h minus 1. All you would need to do is simply just divide, to calculate the autocorrelation, by simply just divide by the variance of the process, which is a constant, because we assume that it's going to be stationary, it's going to be finite as well. And it's not 0, all right, because if it was 0, then it would not be a random process. It would be basically just a constant function, all right, because it would not, yt would not be a random variable, technically speaking. You understand what I'm saying? If you divide the autocovariance by the variance of a stationary process, you're going to get its autocorrelation. Why? Because the autocovariance divided by the product of the standard deviations, the standard deviations are identical at time point t and time point t plus h. So if you multiply basically the standard deviation at time point t and the standard deviation of time point t plus h, because these are going to be identical expressions, you're going to get the variance back. So if you divide basically the autocovariance by the variance, you're going to get the autocorrelation. So therefore, the Yule-Walker equation regarding the autocorrelation would follow, and that's basically the proof, all right? So that's relatively easy to do, all right? Now, if you want to basically have an example based on that, okay, I'm going to look at the first order autoregressive process. We already consider, if the process is stationary, we already considered what the mean, what the variance, and what the autocovariances are. So I'm not going to repeat these steps, how to calculate those. You can use that basically by looking at the inverse of the Lac polynomial, which I would recommend, because from the inverse of the Lac polynomial, you can get those expressions directly by identifying these coefficients, and that's how you would do it for the second order model, as I was, giving you in the next assignment. So for the first order was v by 1 minus a for the mean. You had the variance sigma squared by 1 by 1 minus a squared for the variance, and for the autocovariance you have just simply a to the power of h times the variance of the process. And since basically none of these expressions would depend on time, as I mentioned before, the process is stationary. You might know this, right? So that's something that you might remember. Anyways, I did that, so I'm not going to do it again, all right? But I want to look at the autocorrelation function. So if you want to apply basically the Yule-Walker equation, you will find that the autocorrelation is simply just equal to, with respect to the time lag h, is simply just going to be a to the power of h in this case. Okay, that's relatively simple. I think we did that also, right? So it only depends on basically a to the power of h and on the parameter a and on the time lag. So if basically looking at time lag 1, you'll find that the autocorrelation is equal to the parameter a. So sometimes this parameter is simply referred to the autocorrelation of the process with respect to the time lag 1, because that is a first order autoregressive model. Okay, so sometimes it's simply just expressed by it. So therefore, in most of the time, you know, this parameter is called rho as well, because rho refers to the autocorrelation of the process. This is the autocorrelation, the first order autocorrelation. I mean, you can say the autocorrelation of the model with respect to time lag 1, right? So that's basically it would be. But again, I was not expressing it as such. Anyways, if you look at the Yule-Walker equation, you can simply just get those that you simply just have a times the previous autocorrelation. Okay, so if you look at the autocorrelation with respect to time lag 2, you simply just take a times the autocorrelation with respect to time lag 1. So that's going to be a squared then. All right, so if you basically are aware of that. So you have the autocorrelation with respect to time lag 2. This is going to be a squared accordingly. Then you have the autocorrelation with respect to time lag 3, which is going to be a times a squared. So this is how it evolves, right? So you take basically the previous one and multiply it by a to get the second one. As you see, since basically the absolute value of the autocorrelation, of this parameter, which you can call it autocorrelation with respect to time lag 1, if you see that this is less than 1, right? The autocorrelation is going to be, let's say its absolute value is going to be decreasing. You understand what I'm saying? So as basically the time lag progresses, the absolute value of the autocorrelation is going to be less and less and less, and that makes sense because, you know, as time progresses, the observations tend to have less impact on future observations. All right, I mean that makes sense. So this is typical basically for AR model in general, but especially for the first order autoregressive process. Now I was looking at so-called autocorrelations or so-called correlograms. I'm not sure if you know what a correlogram is. The correlogram is simply just, you know, displaying the autocorrelations depending on the time lag h. So I'm going to put basically the time lag h on the x-axis, that's going to be here, and I'm going to express the autocorrelations depending on that here. And this, I mean, this graph, as you will see, will be the so-called correlogram of the process, okay? The correlogram of an AR process would also tell you a lot of things about the process itself, how the process would look like in general. So there is one way basically to address that from empirical perspective. You can calculate the autocorrelations, I mean the empirical counterparts, and then check whether that fit would basically to your model, but that's something that we are not going to consider. If you have basically, let's say A being equal to negative 0.8, which is the autocorrelation of, the autocorrelation of the model with respect to the time lag 1, that one, so that's going to be the first, right? That's always here. And then you see the others, you'll find that the absolute values are going to be decreasing, right? So as basically the time lag progresses, and that's what you will see here, okay? Now it's going to change its sign all the time, okay? Because, you know, since basically the observation negatively correlates to its previous observation, okay? And then if you go 2 steps ahead, then you will find that the correlation is going to be positive then, okay? Because then, you know, so the second, if you go 2 steps behind, and this observation will have a positive impact on the current one, and the others are going to have a negative ones, all right? So again, that will change its sign all the time. All right, guys? So, I mean, that's not surprising. This is how it would look like if you have, let's say, negative 0.5, which is also relatively large. Then if it's basically 0, or let's say close to 0, it's not always visible, right? Then you have, if it's positive, then it's going to stay positive. So this is how it will look like, typically speaking, for an AR1 model. Now, I was also calculating the autocorrelations basically for an AR2 processes. I'm looking at the correlogram of that. Okay, so you can simply just start by, you know, addressing these just as accordingly, you know, from the parameters which I did. So this is how it would start and this is how it would look like. So if you have a higher order process, the correlograms can have, let's say, a much more flexible structure, as you see. Okay, so the variations are relatively large. So I'm not going to basically address all of them, but as you see, as I change the parameters, right, so you can see here, as I change the parameters or parameter values or even the signs, I can also change the correlograms with them as well. And again, so if you have a higher order process, this allows you a much greater, let's say, variance of these correlograms as that you will see here. Okay, so again, for the first order case, these are how they look. Okay, so it's not a big surprise, of course, but that's it. So this is how it would be. Okay, but again, if you have a high order process, that you might have a different structure, but the tendency here is also clear. Okay, so if you want to, let's say, have greater autocorrelations, you need to have a much higher order processes. Okay, but the tendency is clear. So after a while, as basically the time lag progresses, the impact of past observations is going to tend to be decreasing. They tend to be after a while. Okay, so after it hits some point. But again, this is just for the second part. Okay, so as you know, second lag, and then it's going to tend to be decreasing, at least as far as its absolute value is concerned. All right, but again, it can vary so different ways, and that's what I wanted to demonstrate. All right, it depends also on the parameter as well. Okay, whether the process is stationary or not, I hope they are. So, but that's what this is going to be about.